Hello, so we're going to be talking about bond association and dissociation. So let's go ahead and take a minute. We are going to look at these two examples and you guys are going to determine which would be more stable and why. So you should have chosen B. Now, B is more stable due to the fact that they do have bonds. They are bonded. Where here, these are just atoms with looking for an attraction with other electrons. For instance, hydrogen wants to have 2 valence electrons, oxygen wants to have 8, but it only has 6. So it's very electronegative. It's going to be looking for those electrons, so it's very unstable. So it would need those in order to be stable, the electrons. So let's talk about bond energy. So the energy released when forming a chemical bond, now that is when you form a product. So looking at this reaction coordinate diagram, when you form bonds, this happens on the product side. And the energy required to break a chemical bond, now you get that energy from your reactant side. And I also mentioned to you guys how to look for your change in enthalpy. So what I told you guys to do was to draw an arrow from the reactants to your products. So your reactants are here, your products are here, and if we were to draw an arrow going from reactants to products, that arrow would go down. So that would be negative. And it's for your change in enthalpy. So we would have a negative delta H. So whenever we have a negative, we know that that is an exothermic reaction. So our reaction coordinate diagram is showing an exothermic reaction. Now we have talked about enthalpy of a reaction. So remember enthalpy, your delta H, it's the heat being released or absorbed in the bonds in a chemical reaction. So we have solved for this number, or the unit, remember it's usually in kilojoules per mole or in joules per mole, in a reaction. We've actually already done that when we're going over calorimetry. So we're actually going to do that again, but in a different way. So this is your bond energy chart. If you notice, the units for it is in kilojoules per mole. And what you guys are going to do is you guys are going to look for the bond from C to F. So from C to F, oh, right here, it is 485. And it's kilojoules per mole. Now, that is the bond energy for the C to F bond. Now let's look at the next one. O to C. So you look, O to C, O to C. I don't see O to C, but I do see C to O, which is the same thing. So that one's 358 kilojoules per mole. Right? Not too bad. Now let's look at this one. I see an N with 2 lines bonded to another N. Now the 2 lines, they represent a double bond. So it is an N double bonded to another N. Now if you look over here on our reaction coordinate diagram, this one would not be the answer. The 160 would not be it because that is single bonded. So if you continue looking, I see an N that is double bonded and the one below it is triple bonded, but we're looking for the one that's double bonded. So this 418 would be our answer in kilojoules per mole for N double bonded to another N. N to O, we look at our reaction, our bond energies. N to O, it's single bonded, 201 kilojoules per mole. Now O double bonded to another O. We look O to O, O to O, oh, all the way over here. 495. That would be the bond energy for this one. So yeah, so whenever you see the bonds, you just look at your bond energy, the averages, and you choose that one for that specific bond. So one thing that you are going to have to be able to do is be able to find the bond energies, but for now for molecules, so like for bigger compounds. So the first thing you would need to do is count the total number of valence electrons in the compound. Identify the first non-hydrogen atom listed. Not only is it the non-hydrogen, but it is also the least electronegative. Now, if you guys remember, fluorine is the most. So the one furthest away from fluorine that cannot be hydrogen would be your central atom. Then you would draw the Lewis dot diagram for the central atom first. Then you add the dot diagrams for the non-central atoms. You bond the single electrons and you check your work using formal charge, which is the group number. So which column they're on, minus the lines, minus the dots. Or you can even say group number, you can say valence electrons, minus lines, minus dots. And then you redraw your Lewis dot structure to make it neat, and you would then you would get your Lewis structure. So let's try this one, N to F. So what you need to do is you need to get your periodic table. So I know you kind of barely see me. Remember, each of these columns have specific amounts of valence electrons. So the first column would have 1, second column would have 2. Remember, we're going to skip the D block and go to 13, which would have 3, the next one 4, 5, 6, 7, and your noble gases would have 8 valence electrons. Okay, so looking at nitrogen, I saw that nitrogen had 5 valence electrons. Fluorine had 7, so but 7 times 3, because there's the subscript 3, that would be 21. So 21 plus 5, we would get a total of 26 valence electrons. Now we need to pick our central atom. So our central atom would be the one that goes in the middle. Remember, it is never hydrogen, and it's the one furthest away from fluorine. So because fluorine is part of our compound, that means nitrogen would go to the center. So I'm going to draw N in the middle. And then we would draw our non-central atoms. So our fluorines would go all around it and try to space them out as evenly as possible. And then you add the Lewis dot diagram for your central atom first. So remember we said that nitrogen has 5 valence electrons. So 1, 2, 3, 4, 5. And fluorine has 7. So 1, 2, 3, 4, 5, 6, 7. We do the same thing here. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then, so once we give our Lewis dot diagram, we do the Lewis dot diagram for all the atoms. Now we need to bond the single ones. So use a darker blue. So I see that this one's single, this one's single. We're going to bond them together because they like to mingle. And this one and that one. There you go. And we can check our work using formal charge. So it is your valence electrons minus the lines minus the dots. So for instance, fluorine has 7 valence electrons. I see that there are minus the line, so there's only 1 line. And the dots, there's a total of 6 leftover dots. So that is 0. So these are all the same, so I know that the fluorines are good. Let's check the nitrogen. Nitrogen has 5 valence electrons. Oops. Minus the lines, I see 3 lines. Minus the dots, there is 2. So 5 minus 3 minus 2, that's 0. So I did draw our structure well. And you can just redraw it to make it look a lot nicer. I'm not going to, just so for time's sake. So this would be our nitrogen to fluorine NF3 nitrogen trifluoride compound. We can do the same thing for carbon dioxide. So here are my list of rules. I'm going to go ahead and do like a fast-paced version of it. So first thing to do is count our valence electrons for our atoms. Carbon has 4, oxygen has 6. So carbon's in the center because it is furthest away from fluorine. So carbon, and we would draw 2 oxygens. And remember, we want to draw them kind of as far apart as possible due to, you know, there's electrons around it and they're repelling each other. So carbon, we said, has 4 valence electrons. So 1, 2, 3, 4. 4. Oxygen has 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And if you notice, I like to leave the single ones facing the atom. Now, I already drew the Lewis dot diagrams for each of the atoms. Now we bond the single one. So I see that this one up here, I'll use yellow, is single. It's going to bond with this single one here. This one's here, single, bond with that one. This one here will bond with this one, and that one will bond with that one. All right, so that does look very messy. It's not very symmetrical. So we can, of course, always redraw it. We can check our work using formal charge. So oxygen has 6 valence electrons minus. There's 2 lines. Now, because there's 2 lines, that means it's double bonded. And there's 4 leftover electrons. That's equal to 0. That one's the same one, so it's going to be 0 as well. Carbon, there's 4 valence electrons minus. I see 1, 2, 3, 4 lines on it. And there's 0 dots left over. So our formal charge is 0. So that means we drew it good. There's no any leftover electrons anywhere. So let's go ahead and redraw it. So when we do, we have carbon in the center, double bonded to our oxygens. And then let's not forget to add our leftover lone pairs. So there's 2 lone pairs on the non-central atoms. So we have iodine pentafluoride. So I will go ahead and draw this one really fast. So for this one, from fluorine is iodine. So iodine goes in the center. This one's going to have 5 chlorines all around it. So 1, 2, 3, 4, 5. Iodine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 for chlorines. So I'm going to go ahead and pause it. That way I'll go ahead and draw the valence electrons. So here I drew the rest of the chlorines and I added their valence electrons. I kind of made the single valence electrons a little bit more bold. That way it's easier for you all to see. So I look at iodine and chlorine, and the one that I see for sure I can bond easily, it's this one right here. Now, iodine doesn't have any more lone pairs or any single electrons. So what we're going to have to do in order to, because they're all going to go bonded, is separate a lone pair. So this lone pair on the bottom, I'm going to separate the electrons so that one can go here, one can go here. Oops, that one erased. This one will go here, and this one will go here. And we have one lone pair on the central atom. So that's how you would draw iodine pentachloride. So let's look at this equation. Here we have our change in enthalpy of the reaction equation, where this symbol, the sigma, represents the summation. So it means to add. So it's the summation of the bonds broken, which are the ones on the reactants, minus the summation of the bonds formed from the products. So in simpler terms, the summation of your reactants minus the summation of your products. We're going to use this equation in order to calculate our change in enthalpy of a reaction. So let's go look at the example. Oh, and remember, the bonds are being broken on the reactant side, bonds are forming on the product side. So this is how we are going to solve for the problem. Step number 1, we're going to draw out our Lewis dot structure. We're going to label all our bonds with the bond energy. So we're going to need that little chart with all the bond energies, and then we're going to calculate from our reactants our summation of our reactants minus our summation of our products. Now let's look at this first example. We have nitrogen bonded to another nitrogen because there's the subscript 2. So that means we have 2 nitrogens. So I'm going to go ahead and draw 2 nitrogens. And we still have to draw their valence electrons. So I know that each nitrogen has 5 valence electrons. So, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And then we bond all the single ones. So this one's single, they mingle, single, they mingle, single, they mingle. All right, so I see nitrogen that is triple bonded with another nitrogen. So plus, now we have H2. So we always look at what our molecule is. So we have hydrogen. So it's hydrogen bonded with another hydrogen. I know that hydrogen has 1 valence electron. And then we bond the single ones. Now, because we have a coefficient of 3, that means we need 3 copies of our hydrogen bond with the hydrogen. So I already have 1. We need to draw 2 more because we need a total of 3. And you can see it was a lot easier for me to do it since now that I know how hydrogen looks like. So it's easier just to go ahead and bond. And now for our products, we have NH3. Remember, hydrogen can never be in the center, so that means our nitrogen will be in the center. And we have 3 hydrogens around. Nitrogen has 5 valence electrons, so 1, 2, 3, 4, 5. Each hydrogen has 1. And remember, we bond the single ones, so single, single, single. Okay, so first step was to draw. Next step is to give them the bond energies. So this is where we're going to be needing the chart. So you look at nitrogen triple bonded with another nitrogen. That number is here. Oops. And the number is 941. So 941 kilojoules per mole for this bond from N to N. Now from hydrogen to hydrogen, we have this one here, which is 432. But remember, there's 3 of those types of bonds. And now from nitrogen to hydrogen, or hydrogen to nitrogen, where is that one? Oh, right here in the top. It is 391. So 391, 391, 391. Now, the last part is to use your calculation. So we need to find our delta H of the reaction, which is the summation of our summation of our reactants minus the summation of our products. So that means the arrow is what separates our reactants from our products. So here we have our products. So let's go ahead and add all the numbers that are on our reactant side. So 941 plus 432 plus 432 plus 432. Or you can do 432 times 3 and then add the 941. So we would get 2,237 kilojoules per mole. Minus, now we can do 391 plus 391 plus 391, or 391 times 6, and we get 2,346 kilojoules per mole. And we subtract them. So when we subtract them, we would get our answer for our delta H of the reaction. So when I do, I get negative 109 kilojoules per mole. That is our answer. And because our delta H is negative, that means we have an exothermic reaction. Now let's try example number 2. So here we have H2 plus, this is chlorine, Cl2 would yield 2HCl. It's also chlorine. So hydrogen plus chlorine would yield hydrochloric acid. Okay, so step number 1 is to draw out our molecules. So we have hydrogen, we have 2 of them, so 2 hydrogens. Each hydrogen has 1 valence electron, and singles, they like to mingle, so we're going to go ahead and bond them. And since there's no coefficient, that means there's only 1 of them. Plus, now we have a chlorine bonded with another chlorine. I know that chlorine has 7 valence electrons. So I'm going to go ahead and draw my 7. And again, singles like to mingle. There's also no coefficient in front, so that means there's only 1 of them. And we would yield HCl, so HCl, hydrochloric acid. So 1H with the Cl, which is a chlorine. Chlorine has 7 valence electrons. Hydrogen has 1, so these single ones that like to mingle. So we'll go ahead and bond them there. Oops. But because of the coefficient 2, we need 2 copies of them. So I would need another hydrogen and another chlorine. And then just go ahead and draw your valence electrons. Okay, so step number 2 now is to label our molecules with the bond energies. So for hydrogen with another hydrogen, the H to H bond, it's this one right here, which is 432. And then we have Cl to Cl, so chlorine to chlorine, that is 239. And if you look closely, it's right here, this one right here. It's right here. And then from H to Cl, hydrogen to chlorine, that's right there, that is 427. And it's for each bond. And remember, our delta H of the reaction equation is the summation, oh my goodness, summation of our reactants minus the summation of our products. So you would have to add the 432 plus 239, and when we do that, we get 671. And then we subtract the summation of our products, so 427 times 2, or 427 plus 427, that is 854. Oh, and don't forget our units, kilojoules per mole. Kilojoules per mole. And that equals to negative 183 kilojoules per mole. Now, this is our delta H of our reaction. And because it is, again, negative, that means this is an exothermic reaction. Let's look at example number 3. So with example number 3, this is the third one we see, so I am going to go a little bit faster. So here I have 2 different atoms. Remember, hydrogen can never be our central one, so that means our carbon goes in the middle. But we have 2 carbons, so the 2 carbons go in the middle. Now we have to draw our hydrogens. Our hydrogens, they want to go on the outside, so far away as possible. Hydrogens have 1 valence electron. I know carbon has 4. And then we bond all the single ones. So let's bond the hydrogens first. We at least do 1 bond together for each molecule because you know they're all together. And I still see a single one up here and a single one here. So let's go ahead and bond those. And this one to this one. Okay, so now I have the C2H, and I have a triple bond now here from carbon to carbon, and then a single bond from carbon to hydrogen. So that's plus. We have our hydrogen to hydrogen. So H bonded to H, and we would have 4 of those copies. And this would produce C2H6. So again, remember hydrogens can never go in the middle, so it's the carbons, there's 2 of them. And we would have 6 hydrogens all around, so I will just go ahead and put them far apart. Carbon has 4 valence electrons, hydrogen has 1. And it will look like that. And if you see 1, 2, 3, 4 on the carbon, 1, 2, 3, 4, each hydrogen gets 1. So, oh, and not only that, but we need 2 copies of this one. Oh, and I already made a mistake. Why'd you all tell me? We need 2 of the C2H2. So I'm going to go ahead and draw another one of these. And then C2H2, I'll draw another one of those. C2H6, sorry. Correction. Okay, so yeah, we're gonna have to use a lot of bond energies for this one. So let's go ahead and look from C to H. This is a single bond. So from C to H, it is 413. So 413, 413. And I'm only doing that to C to H bonds. And I do see more on this side. Okay, I'm gonna go ahead and pause. Okay, so I did all the C to H's. Now the C to C, carbon to carbon, the triple bond, if you look here, it is 839. And our hydrogens, it's 432. Okay, so everything's all in place. Now we just need the carbon to carbon bond. So from carbon to carbon is 347. So just do a double check, just make sure that every single bond is labeled. All right, so I went ahead and did that. This is where we're going to divide. Remember, it's our delta H of the reaction is the summation of the reactants minus the summation, this is a minus, the summation of our products. So remember, our reactants are on the left, our products are on the right. We're going to add all these numbers up. So we can already do 413 times 4 plus 839 plus 839, and then plus the 432 times 4. We add all that up and we get 5,000. I will use blue. We get 5,058 minus, now we do the products. So I see 413 times 12 and then plus the 347 plus 347, we get 5,650. And remember, our units are in kilojoules per mole. When we subtract that, we would get our answer. So we would get negative 592 kilojoules per mole of the reaction. That is our answer. All right, so that is basically it for the video. If you have any questions, just please let me know. You can email me or message me if you need any help. All right, thank you.